Welcome to the HiRSE Summer of Testing. This is a collection of tutorials focusing only on testing and is a separate series to the usual HiRSE seminar series.
Hello everybody and welcome to my talk, Introduction to Continuous Testing for Scientific Software. In this talk, I'd like to give you a bird's eye view on how continuous testing can improve the quality of your scientific software. Before we start, let's take a look at the software development cycles with its 6 stages. So we start here at the right in the green box in stage 1 with the analysis, followed by stage 2, the design of the algorithm, the most important one, stage 3, which is the implementation of the algorithm, and which is important for this talk, is stage 4, testing, followed by stage 5, deployment and maintenance in stage 6. After one cycle is finished, usually one feature is implemented and the cycle starts over again with another feature or improvements or refactoring. So the main question is, why do we need testing? I want to start with a quote by Dijkstra, which goes like this: "If debugging is the process of removing software bugs, then programming must be the process of putting them in." So basically what he's saying is that after programming starts, a lot of debugging sessions will follow to get rid of all the errors and bugs you put in while programming. So let's take a look if we can simplify that or improve upon that. The first part of this talk will be about testing itself, and the second part of this presentation will be about the continuous part of continuous testing. So let's start with part 1, testing. So from the quote I just showed you, you could see there's like two things: debugging on one hand and testing on the other. So you might think this is the same thing, but actually it's not. So debugging stands more or less for error correction, and testing stands more or less for error detection. And obviously it makes sense to remove bugs or errors in your software as early as possible, and you can do that ideally with tests. As you can see in the first box here, there's several different kinds of tests. There's tests that can be done by the developer, so-called white box tests, which basically allows you to take a look inside of the code you want to test. So it's not like a black box where you don't know how the internal machinery looks like. And the other kind of tests, like black box tests, that can be done by specialists or other team members in your group, where you don't take a look at how a feature or functionality is implemented, and you just use it as a black box and test it as a black box. In this talk, we mainly want to talk about the first kind, so tests you can do as a developer yourself. On the right, you can see how scientific code should work. So usually, if you write code, the most important thing is it should be correct. If it's not correct, we obviously don't get the results we want, so it doesn't make sense to execute it at all. And in order for code to be correct, there's a certain set or certain sets of tests that you can do. And in the second box, you can see I wrote down some of the tests that can be performed on that test. There's unit tests, component tests, integration tests, regression tests, and system tests. And we will talk about all of them at a later point. But there's also some more tests you've heard about probably, like beta tests, performance tests, configuration tests, and stress tests. And the reason for this manifold of tests is that we not only do have correctness as a goal for our code, we also have other goals. For example, if you work with code on a supercomputer, you want the code to be fast. If you work on different machines or you have a larger user base, one uses, for example, a Windows machine, another one uses a Linux or a Mac, you want the code to be portable throughout these operating systems. If your code has to run on different hardware, obviously it has to be portable as well. And all these things need to be tested in order to work. If you don't test them, you cannot trust the code you write. So obviously it's a good thing to test as much as possible. So at the end, it boils down what we want to do. How do we want to spend our time coding? The main idea of writing tests is basically to reduce the time you spend in debugging, because most of the stuff has been tested before it is shipped out. On the right, you can see I added 2 more boxes that are not necessarily part of the let's say, importance of the scientific code, but this is something you want to add to your code in order to make it more composable or more maintainable. If we talk about testing, obviously we have to talk about bugs. And on this slide, I will show you an interesting insight on how the actual size of the code base impacts the number of bugs. So usually you would think the number of bugs just depends on the number of lines of code you write. So it's a constant. If you write 1,000 lines of code, you have maybe one error in it or one bug in it. If you write 2,000 lines, it's like 2 bugs. But as you can see here in this plot, it's a little bit different. On the x-axis, you see the lines of code. So we start at 2,000 lines of code, and the last bar plot is for codes with more than 500,000 lines of code. We have a blue bar and a red bar. The blue bar is basically the minimum of bugs that the study has found for a certain code base, and the red bar is basically the maximum of bugs that had been found in that study. And on the y-axis, you get the number of bugs, but not the total number of bugs, but the number of bugs per 1,000 lines of code. And what you can see is you would expect that this number stays constant, so independent of the code size, the number of bugs only depends on the number of lines. But what you can see is that the number of bugs increase. So basically, this means if you have a large code base, you will have much more bugs than if you would have several small code bases. So then the bugs per lines of code basically depend on the project size. And the bad news is that the total number of bugs increases quadratically with the project size. So the important thing to learn here is that you should structure your software in a way that you basically have a separation of concerns, that you split up projects into smaller independent projects that can be maintained separately in order to get the number of bugs as low as possible. You could ask yourself, why should I write tests at all? So think about the following fact. You have a developer team, and the main question you could ask yourself, how persistent or how experienced is your developer team? Most of the time you have like one core developer, at least in scientific projects, which is usually staff, that deals with this project for a long time, usually years. Then you have some master students and PhD students that contribute to the project for a certain amount of time, usually 1 year to 3 years if it's a PhD student. And then you also have guests that join you in the project, which is more on the short term, a few months up to a year, I would say. And the main problem with that is usually the staff member is the one that maintains the code, and after the master student left or after the PhD student left, maintaining the code or maintaining their code or their feature is up to you because they're out of the project. And the second question you could ask yourself is, do you trust your developers unconditionally? So some questions that might come up are like, is the code correct in all the required cases? Or did the person that wrote the code just test for a special case he needed? A second question, which is also really important, who do you ask if a developer has left, if something isn't clear in the code? And the third question could be, is the provided code in a reusable or an extendable state, so other people can understand what has been written and can extend it easily? All these questions basically come down to, let's write more tests, because if there's a test for something, you can look into that code and see exactly what's going on and check if it works as expected. The second slide of reasons why tests would make sense is, just imagine you're writing a library or you're using a library. And the question then is, do you trust that library? Or if you're writing a library, do other people trust yourself that you did everything right in your library? Basically asking the question if the code quality is good enough. They may ask themselves, do I trust the code without verifying it? And you can ask yourself the same thing if you use a third-party library. And if you provide a library, other people might ask themselves like, hey, is it worth to put some effort in and base my work up on that software, or is it buggy or in a state that cannot be maintained? So it's a waste of time to base my software up on that. And this all boils down basically to the currency of science. What's the currency of science? Usually it's papers and citations. And in the last years, code sustainability is also something that came up more and more. And the reason for that is we don't want to reinvent the wheel, and we don't want to write code that somebody else might have written already in a good state. So reuse is a good thing. Another reason that is related to the currency of science, the papers and the citations, is basically shown on this slide. So there's a paper called The Scientist's Nightmare, Software Problem Leads to 5 Attractions. Basically, this is also related to missing tests in a part of the software that did the analysis, and 2 columns had been flipped. So the results were presented completely wrong. And obviously, this is something that needs to be avoided at all costs when doing science. The question now stands, like, if tests are so important, why aren't there more tests? And the reason is testing itself is not a trivial activity, because for most of the time this is counterintuitive. When you write code, you basically expect it to be right. If you write a test, a successful test basically means that it fails your software or breaks your software, because if it wouldn't do that, then the whole test would be useless. If no tests ever fails your software, then you wouldn't need to write it. So basically the mindset is really important, that you, when writing a test, make sure that you test all corners of your software and all corners of your boundaries in order to really find errors in the code. The other problem with tests is that even if you wrote like 100 or 1,000 tests, there's still no guarantee that the whole program is free of errors. You could have missed part of it. You could have tested other things more than once. So this is also a downside of tests. And the other thing is, a test itself doesn't improve the software quality. It's basically just an indicator for software. But if you don't change the software afterwards, or if you don't find bugs, then the software is still in bad shape. And the main reason, I would say, is it takes some time to develop good tests, so you can use them in the right manner. Okay, so if we want to write tests, how should we ideally do that? So in my opinion, it's really important to do it like this. You would write the test first before you even write a function or a class or whatever. The reason for that is this helps you to think about more of the design of the code itself. Because all the requirements that come up in an interface or in that class can be highlighted at an early stage, and you don't go down a rabbit hole where you later won't have to refactor the whole code. It also simplifies the test case, because if this is the first thing you want to think about even before writing the code, obviously you want to write a simple test. And this helps you with separation of concern, because you do only try to test one thing, and your class would then only consist of one thing, which is a good design pattern. And if you do that, bugs can be detected earlier because you designed the tests, and if something unforeseen happens, then you can see, oh, something is wrong in the design. There's also some pitfalls when doing that. You have to make sure that the coverage of your code is really large, ideally 100%. And by coverage, I not only mean that all the statements in a usual run are covered, but also all branches. So if you have like branches in your code, you have to make sure that your tests cover both branches in the code. The other thing that is important, if your code changes, so basically if you do commits and the code changes, the tests itself need to adapt if the functionality, for example, changes. And one good thing to do is usually to make the code changes as small as possible, so it's easy to track if something goes wrong or a bug occurs. The other question that usually comes up if you're not dealing with new code. Most of the people deal with legacy code, and usually if you write legacy code, there's not many tests available. So the question is what to do about it. And as we've seen on the first slide, the software development cycle basically cycles through all the 6 stages over and over again. So at one point you will be refactoring some parts of the code, for example, because you add a new feature or improve a feature. And this refactoring phase is a good starting point to add tests. So even if you're working with the legacy code, at some point you will be at a stage where you rewrite code or write new code, and this is the ideal point to also start with testing. If you write new code, on the other hand, it's a little bit easier because you can basically apply the solid design principle when writing code. And I'm not going through all the letters. The most important one for testing is basically the first one, the S, which stands for single responsibility. So you figure out what the smallest unit of responsibility you want to deal with. This is the class or the function you want to write. And before doing that, you basically write a test for that, writing the class afterward. After that, both of the algorithms or both of the codes, if you write legacy code or if you write new code, is basically the same. You start with writing a test. The test will obviously fail because you didn't write any code, so the test can be correct. Afterwards, you start with the new code or the new feature. And at some point, the test will be correct. And then you can start refactoring and make sure you, for example, improve for speed or you extend to a different architecture. But the test itself will be there and can be reused in all these steps. In the beginning, I did show you that there's like several different tests. On the following slides, we will dig a little bit deeper on how testing should take place. And I also provided an overview how usually people test and how testing should be performed. So let's start with the first test, which would be unit and component tests. So unit test itself is very simple. It basically only tests a class or function. So this should be really on a small scale, and the test should be in isolation. So this class shouldn't be tested with other classes around or depending on other classes. It should be independent of any class that uses it. And usually this is the part where most of the developers don't have any tests, but this is also the part where most of the tests should be there, because if you write, let's say, something low level in a unit, obviously this will be reused very often, and if the error is in that part of your code, this will propagate, and if you would have tested it, you would have found the bug earlier. The other tests that are on a lower level is like integration tests. If you, for example, wrote your class, tested it, and you wrote another class, tested it, you're done with the unit tests. Now you can write integration tests that basically provide a combined test of multiple classes. So you basically test these two classes together. Does the interface work with the class? Again, usually people don't write many tests here, but again, since it's on a very low level, you should write quite a few more tests. On the higher level, it looks a little bit different. We do have like system tests, and this is what most people do. You have a final software product, and obviously you know your input data, you know your output data, and most of the people test that because they want to make sure the simulation they're running does work on a specific hardware, and a lot of tests are available at this point. System tests also includes integration with other external software, so you could use libraries you'll depend on and test your full product. System tests should be performed for everything that couldn't be tested on a lower level. That's somewhat obvious. If you can test something on a lower level, you should obviously add more tests on a lower level. Another class of tests that is really important is regression tests. So basically, a regression test tests something that in a previously developed version was still correct and now it fails. And basically you can think of it, if you have a bug in your code and you write a bug fix, you should also write a regression test that basically fails on the old code and doesn't fail on the new code. So if the regression comes again in a new commit, you have that covered. And people usually don't write regression tests. And if people write regression tests, they throw it out after it works. So you should keep that in. So that's really important. If you write a test, don't throw it out, keep it in. So all the software development takes advantage of that regression test. The other advantage of keeping regression tests around is you get a nice record of the most common defects in your software. So if you see, for example, you have a tool that parses some input data and another tool that computes stuff, and you see that most of the errors do come out of the parsing tool, obviously you can take more care and then concentrate your work on the part of the code where more defects come from. So usually it's not the case that all the bugs are distributed equally among your or inside your code. Usually there's like a hotspot area, usually the most complicated things where defects are. Okay, so the main question now is, how do we check for code quality? And ideally we check for code quality through test coverage. So what we want to make sure is that all the lines of code we write are covered by some tests, so we are not losing anything. So how can we think about quality of software? So I would say that untested or uncovered code should be expected as wrong because you didn't test it. Technically, it could be anything, so make sure that your test coverage is high. If this is hard to write a test for something, this is usually a good indicator that your code is a little bit too complex and you should split it further apart and introduce some internal interfaces. And if you want to go the extra mile, it's even better to decouple code parts into separate libraries. For example, if you have a simulation that also reads in some configuration file in an XML format or something, it's a good idea to extract it into a separate library. This also helps you at some point, for example, to replace it with something else if this better fits your needs. This is hard to do if everything is like a monolithic block fused together. If you write everything into separate libraries, this makes much more sense. It's also important that, as we have seen earlier on the slides, you test on the smallest possible units, so down to basically every function, because this is the level where you understand what's going on, and if you use this as a building block on a higher level, you can make sure that there's no errors that propagate. If every line of your code is covered, then it's very likely that you will find the bugs easily. And obviously there's also tools where you can take a look at the coverage, so you don't need to do that in your brain. There's tools like GNU GCOV that basically helps you and visualizes how much code is covered and even which part are covered, so you know exactly what tests are still missing and what code you still should write. At one point, if you're restructuring your code, this is also much safer if there's already a test in place, because the functionality should be the same and restructuring should just make it cleaner, more maintainable, and the test should still be correct. And if for some reason you miss something and a bug occurs, then you immediately see what's going on if you test. One thing I personally find very important when writing tests, usually people write tests and usually people write code and documentation. But at some point, if you restructure the code, the documentation might be outdated, so it doesn't fit anymore to the code you wrote. And sensible tests are much better in that a test is basically easy to read, and since it's not allowed to fail, it will not be outdated. So at some point, I would say tests are much better than documentation, because if they're written in an easy way, it's easy to understand, and even outsiders could understand that, and it will not get outdated because it has to make sure it does not fail. After we covered the first part of testing, let's go to the second part of continuous testing, because up until now, all the tests you wrote had to be executed manually. And obviously this is tedious, and if you have to execute something manually, you will not do it as often as necessarily. And with continuous testing, we basically can find a workflow that helps us doing everything automatically. How could continuous testing work? Okay, the good thing is that after setting up continuous testing, it's readily available. So you can run things more frequently in the background, so you don't need to wait for tests to finish. And you can do that on every commit you do on your software. So you write a feature, commit the feature, in the background the tests will be executed, and you will see if it works or not. The advantage is that while you develop your code, in the background the test runs, and if there's a bug, you can detect it early and also minimize the work you have to do in order to fix the bugs, because the function you wrote is fresh in your mind and it's easier to dissect what's going on. On the bottom, you do see basically a graph on how you could do that. First of all, as we discussed earlier, you would implement your test, commit it to the repository, then you would implement your feature, commit it, then the auto test would start, and there's like two outcomes. If everything is okay, then you could merge your commit into the main branch and start implementing the next feature, or if it didn't work out, you can fix the errors, commit it again, wait for the auto test to finish, and test or check until the code works correctly. And once it works correctly, you can merge it and go to the next feature. So this really makes sure that everything you write is correct in the first place if you implemented the tests correct in the first place. In order to allow for continuous testing, we have to set up an ecosystem for that. So the first thing you need in your code is an automated build process and dependency management. So you basically need a makefile or CMake or Ninja that basically automatically can build your code. So if you can type in make on your command line and the code builds automatically, this is already important for automatic testing, because if we want to automate things, obviously we cannot type in all the commands by ourselves. The second thing we need is like change management and continuous integration tools. So the first of it would be a version control like Git or SVN, and ideally you also have a ticket system where there's a bug tracker involved. So if external users that basically found a bug or a probable bug can provide you information on what's going wrong. The second thing you need is a testing framework that can help you with setting up these tests, because most of the stuff you don't have to do yourself. You basically can use testing frameworks like Google Test or Catch2 to help you with automating tests. And last but not least, you need a CI. And GitHub or GitLab, Jenkins, TeamCity, these are all examples that are freely available, which you can use in order to run your tests. So you can basically define what should be tested, when should it be tested, and what should happen when it fails or if it goes through. One more thing that people usually don't think about when setting up these CIs, you also need resources that basically can get used for these tests. If you use GitHub, for example, you do have GitHub Actions where you can run small scripts and test them directly. But if you have larger codes, you probably have to provide resources yourself, or university or your research institute already has something set up for you. So this is something that is usually not available online for free. And as cherry on top, I would say is something like a package manager. In this example, I give you the example for C++. So there's like Conan or VC package, where you can build packages out of the software. If you're coming from Python, obviously you can use pip directly. But this also helps to provide software in a maintainable form and in a composable form where others can use it, and helps with sustainability. On this slide, I want to give you an example from my past. So basically, we started also with not testing much. Here you can see a test matrix. Basically, on the top, you see different compilers we wanted to test for. We have the GNU, C++ compiler, Clang, and Intel compiler. We tested for different floating point types, float, double, and long double for each compiler. And on the y-axis here, you see some other dimensions we tested. For example, the x86 hardware, we tested make and ninja, debug and release mode, and then some settings for our code that could be enabled or disabled. And the only thing we tested back in the days was just one setting. So x86, release mode, upper settings, FM solver, PAPI settings, and only double. And usually you would think, okay, what could go wrong? But if you test all of this matrix, it looks like this. And the nice thing you see here is that usually it's not like there's like one thing not working, there's usually a pattern. And the pattern you immediately see here, all the float tests independent of the compiler failed. And this basically showed us that we had some overflow in our floating point representation. We had to fix that. It didn't came up in all the double and all the long double computations. And it's even independent of the compiler, so you see this is a real implementation bug. And after fixing that, the whole matrix would be just okay, and all this stuff works well. One thing, however, you need to think about is the combinatorial explosion of possible tests. So as you have seen on the slide before, there's just a few variables, and on this slide I just wrote a few more. And this is not even variables that is related to your code. This is just related to your software environment and your hardware. So as you've seen on earlier slides, for example, if you want to be portable, obviously you want to test on different CPU architectures. So in this case, I used 5 different architectures. You want to test for different floating point types. I used 4 different types. So we already have 5 times 4 tests. You could also add different microarchitectures, because if you're going for speed, then obviously the microarchitecture plays a crucial role. So you would have another 5 tests, or another dimension with 5 tests. And if you look at the software side, you could test with different compilers, another 3. You could test for debug and release mode, or you should test. You don't need to test for different build systems, but you could do that. And sometimes you even need to test for different compiler versions. And this obviously explodes really quickly. And you cannot test everything in this matrix, because just imagine you do a commit and your test takes longer than you do the next commit. Then obviously it's really hard to keep track of all the stuff that works or doesn't work. So you have to make sensible selection out of these things, and probably you have different selection, but it's easy to go into that combinatorial explosion. Test automation. So how can this look like? Basically, if you have these 3 things, so you have a Git for version control, you have your CI and your tests, you can set it up in a way that for each commit, the test starts automatically. So you don't have to do anything. Once you commit and once you push to your GitLab or your GitHub, the test will, or all the tests will automatically run and will give you a result. As you've seen, the test matrix can be really large, so you have to make sure that all your tests are really short. and don't take a long time, so usually in the realm of seconds, I would say. And the test should also explain the correct usage of a piece of code. So with that, you save the documentation. And that we need a sensible test matrix is obvious. If you do a code review, which is usually the case if there's more than one developer, you should make sure that at least one branch, so the main branch, passes all the tests, so nothing will get merged into the main branch if the test fails, because otherwise your software is broken. So make sure to test on feature branches everything you can test before you merge to your master branch. So let's conclude. We've seen that if done correctly, tests can even be better than documentation that can get stale over time. Tests always basically stick to the code, and if you write it in a clear manner, it's much easier to read and for new people easier to get on track. Tests can also help tremendously to modularize your large code bases. So if you have a legacy code and you think about writing tests, that's a good step, because when you think about it, you will split it into more sub-projects and sub-parts, and this will be easier to maintain. And tests also keep the components really simple, because if you have to think about a test, then you want to make things simple. So the component itself needs to be simple. Continuous testing, on the other hand, is really matured in the last years, because there's a lot of open source tools available that you can use. Unfortunately, the setup costs, so the time to set things up, are high, because obviously you have to write the tests, you have to implement that within your CI. But once you did that, all the automation does its magic itself, and this compensates for the high initial costs, and you will get something out of it because you immediately see if something breaks. And I would also say that continuous testing is somewhat mandatory for projects with 2 and more developers, because you want to make sure where the error does come from, and that you don't introduce any errors in the code. And then it's hard to figure out, is the problem on my side, is the problem on the other side? So if you have something like continuous testing for larger projects, this will tremendously simplify code development. And with that, I'd like to end on a joke. So you usually know that XKCD comic, the #1 programmer's excuse for slacking off. My code is compiling. So you've read that, and I hope in the future that the new #1 excuse is not compiling, but auto-testing. And with that, I'd like to thank you for listening.
Thank you for watching this tutorial. Please check out the slides on Zenodo, linked below, and see you next time.